Good afternoon, good morning to everybody, and we are going to begin with this double session with the participation of two young researchers. And the first one is Cristobal Merono. Thank you very much for accepting to participate in this web seminar. And the title of his talk is the fixed angle scattering problem with the first order perturbation. So let's begin. Let us listen to his talk.
Okay, so thank you very much to the organizer for their very kind invitation. So I'm going to speak about the fixed angle scattering problem, and this is a joint work with later Potenciano Machado and Mico Salo from the University of Jyväskylä. So basically, the problem I want to tell you about is we are going to have a certain potential in Rn, and we are going to send waves that propagate from some fixed direction omega. So the waves are going to arrive, interact with the potential, and they are going to be scattered away. So the inverse scattering problem deals with trying to reconstruct the potential from measurements of these scattered waves. Okay, so before going to the inverse problem, we need to understand the direct scattering problem, which is just trying to understand how actually waves are scattered by the potential. Okay, so here the propagation of waves is going to be modeled by the stationary Schrödinger equation. So basically we have the Helmholtz equation minus Laplacian minus lambda square. Here we have the potential, and we are going to look for solutions that are a plane wave with wave number lambda and incoming from direction omega plus some perturbation. The plane wave is solution of the free problem. So this scattering solution, US, is produced actually by the presence of the potential. Okay, actually, this problem is not well posed as this. One needs to add some restrictions, some technical conditions in order to really model scattering equations. But if you do these things correctly, basically the main thing that we need here is that these scattering solutions, when x goes to infinity, are going to have this asymptotic behavior you have here. So they are going to behave as a purely radial function times a purely angular function, plus some lower order terms. You can see that this radial function is independent of the potential, so all the information of the potential is here in the AQ function. Okay, so the inverse problem, well, this function AQ is called the far field pattern, and basically is the angular profile of these scattering waves. And the fixed angle scattering problem consists in trying to recover the potential from knowledge of this function for a fixed omega. So this is why it's called fixed angle scattering problem. The direction of the waves are going always to come from the same direction omega. Okay, but we measure this for all wave numbers above certain lower bound and for all possible directions. So we look the scattering solution in all possible directions. Okay, so the first step in the inverse problem would be a more basic question that if we want to recover Q, at least we should have injectivity here of this mapping Q to AQ. This is the uniqueness question, because basically it's to ask that this far field pattern is something uniquely assigned to the potential Q. Okay, so this is actually what I'm going to talk about here, and is still an open problem. So let's see about what we know about this problem. The first thing is that one knows is that if the scattering data or far field pattern, I'm going to use both names, is 0, then the potential must be 0. Okay. Then we also know that from results from the 19th of Stefanov that in dimension 3 one has generic uniqueness. That means that at least in an open and dense set of potentials, the mapping is going to be injective. There are also other results in this case of uniqueness for small potentials. So if we assume that the potentials are small in some norm, actually one has uniqueness and also reconstruction. One can give an explicit algorithm to reconstruct the potential, also for low regularity potentials. There are also recovery of singularity results that basically try to, okay, maybe we cannot recover completely the potential, but at least we would like to know where the main leading singularities are, and questions like this. Okay, so the most recent results that have been a breakthrough in this problem are from Mikko, Salo, and Rakesh. And well, this are two very long papers with many results, but I would like to choose two results that are important for this talk. The first one is the following. If we have the potential, if we consider potentials smooth and compactly supported, and we assume that we know the fixed and scattering data for some direction, for example, the vector E1, and we know also the fixed and scattering data for the opposite direction, then this uniquely determines the potential. So the mapping Q to this pair is injective. Okay, this is what I'm going to call a two-measurement result, because we need the fixed and scattering data for two independent vectors. Okay, they also give one measurement results, because they prove that if the potentials actually have some symmetry related to the variable in this direction, in this case x1, or anti-symmetry, then the potential is uniquely determined. So we have injectivity of the mapping, okay, with only one measurement, only with knowledge of this function here. And also this works also if it's a small perturbation of asymmetric or antisymmetric potential. Okay, so in this talk I want to see what happens when we have also the presence of magnetic fields. We have a magnetic potential in the Hamiltonian or first order perturbation. Since this makes many of the computations and formulas a bit more technical, before going into these results, I would like to review a bit some of the ideas used to prove these two results I've just stated. So the first idea that Mikko, Salo, and Rakesh used is to prove that actually the stationary scattering problem that I have introduced at the beginning of the talk is actually equivalent to a time-dependent problem, to a inverse scattering problem for the wave equation in time domain. So they basically show that uniqueness for this problem implies uniqueness for the other problem. So let's see which problem would be this. So we are going to have the wave operator here plus the potential, and we are going to look for solutions that when restricted to t less than -1 are basically this free wave, this delta wave, supported in a plane that is propagating with speed 1 in the direction of omega. Okay, so here the potentials are always going to be compactly supported in a ball of radius 1 to simplify everything. Okay, so this equation has a unique solution in distribution, and basically they have this structure. The solutions are always some function u times the Heaviside function plus the propagating delta wave. And this u function, that is what actually depends on the potential, must satisfy the wave equation when t is strictly bigger than x dot omega, and when restricted this u to the plane t equal x dot omega, it satisfies this. So it's going to be an integral of the potential. Here we are integrating the potential along straight lines that go in the direction of omega. Okay. So this would be the direct problem they have. So in order to state which is going to be the inverse problem, let me have this picture here. So I'm going to put the spatial variables in the plane, and in the vertical direction the time variable. And this z variable here is just the variable in the direction of omega, where the waves are propagating. So since the potentials are supported in the ball of radius 1, which I'm going to call it P, I'm going to define this cylinder partial, which is basically the boundary of the ball times this interval in time. So is the cylinder that you are seeing. So the inverse problem is the data in the inverse problem is going to be the measurement of u at the boundary of this cylinder, sigma. Okay, since actually u is supported for t bigger than x dot omega, actually is supported here in sigma plus, only in this part of the cylinder. Also, I'm going to introduce the following notation. Let gamma is going to be this part of the plane. This plane t equal to c, so is t equal to x dot omega, is the plane where the delta wave is supported. So I'm going to call gamma the intersection with the cylinder, this region here. Okay, so let's. So the inverse problem would be to reconstruct Q from measurements of this function at the boundary, and this is equivalent to the stationary scattering problem. Okay, so let's go to see some of the techniques they use. So basically, the main idea is to use a Kaleman estimate in this region, in the interior of this region, sigma plus that you are seeing here. So let's see. I don't want to go into the details, technical details that are here of the Kaleman estimate. Mainly the idea is that using Kaleman estimate methods and some energy estimates, one gets to an estimate like this. Here we have the exponential of phi is the weight in the Kaleman estimate. And here this sigma is some real parameter that is going to be large in order to this estimate to be true. So in the left-hand side here, you can see that we have a term that involves an L2 norm over gamma. This is the plane, remember, in the cylinder. We have also some ugly terms that involve integration over gamma. On the right-hand side, we have an L2 norm, and we have the wave operator. And the last term is an H1 norm on the boundary of the cylinder. This is exactly where I say that we are going to measure the data. So one needs to get to this Kaleman estimate. There are many restrictions on the construction of the weight, but the idea is then to use this Kaleman estimate that holds for a general function W plus, and now use it for this function. We choose W plus to be the difference of two solutions. Recall this U1 and U2, let me go back, sorry, is basically the function that appears here in the time-dependent problem. This is the scattering that is produced by the delta wave interacting with the potential. So U1 is when the potential is Q1, and U2 is when the potential is Q2. So we take this difference of solutions, and basically one can very easily see that then the wave operator in Q1 of this difference is bounded by the difference of the potentials. And also this operator that one has here on the boundary gamma on the plane is also related to the difference of the potentials. This is because, sorry to go back, we had this formula of the restriction of these solutions to this boundary exactly, and that involves the potential. Okay, so using these two things, one can actually see that then you get the difference of the potentials here, and you can absorb in the left-hand side. So in the end, after all this work, you get to an estimate where you have the difference of the potentials in the left-hand side, and in the right-hand side, you have the term in the boundary. And since this is the data, the uniqueness assumption, we are going to say, okay, if U1 is equal to U2, this means that, okay, this is exactly 0 at the boundary, then we would like to have that Q1 is equal to Q2. So you see the enemy here is this term. And the presence of this term is the reason that one cannot actually get the uniqueness result for the complete the fixed angle scattering problem, and one needs two measurements. The idea is that we are going to be able to cancel this using now waves that propagate from the opposite direction. And how is this accomplished? Well, basically, what we are going to do is to construct, to make a new Kaleman estimate, which is basically the same Kaleman estimate in this region here, in the opposite region. Okay, this is what Mikko Salon brackets do, and they define now the function that take for this Kaleman estimate is now the difference of these solutions, but now they are incoming from the opposite, generated by delta waves that came from the opposite direction. We have here minus omega. So one can see that the Kaleman estimate is exactly the same, except for one thing. Since now the orientation of gamma in this term has changed, actually one has one minus sign. So adding these both estimates, since these terms that one has inside this integral are actually quadratic on W, one can finally bound this really bad term by this difference of W plus and W minus. So here is very important now to use that these are exactly the opposite solutions, the solutions that came from the opposite direction. Because one can now, if one writes exactly what is going to be this in the boundary gamma, we saw that we have this integral formula for the value of this solution restricted to gamma. And actually, you are going to get one integral here for W plus, and this integral for W minus. So in the end, the idea is that one gets here a complete integral. And this is a quantity that even, it doesn't look that way, this is a quantity that we are measuring at the boundary. Because since the potentials are supported in the interior, actually this integral is the same as this if we take x at the boundary and not at the interior of gamma, at the boundary of the cylinder. So in the end, this is something that we know that is zero because of the uniqueness assumption that these solutions are the same at the boundary. Okay, so this is more or less the idea of why we need two measurements, and they basically are used to cancel these terms in the Karleman estimate. So let's go to the magnetic case. So here, the stationary scattering problem is basically formulated in exactly the same way. One just changes the Hamiltonian now to be this Hamiltonian here, the magnetic Hamiltonian that appears in quantum mechanics. So we introduce this magnetic potential A, that is a vector. And basically now the Hamiltonian is minus Laplacian. We have a first order term, and then we have this zero order term here that involves both A and Q. Now, the scattering data can be defined exactly in the same way. So now this scattering problem will to try to recover both A and Q from the knowledge of this data. But there is a fundamental physical abstraction here that is gauge invariance. If you have the Hamiltonian of some function u is equal to v, then the Hamiltonian, where now we have a plus some gradient of a function, is the same of u is equal to v if we put these phases here, exponentials of where f is this function that we have introduced here. So if f is compactly supported in the ball of radius 1, essentially you cannot see this very far away because at infinity, because this is essentially 1. So this means that you actually cannot distinguish from measurements between these Hamiltonians. So this means you can recover A only modulo Adina gradient. So this means actually that you just can recover the differential, the exterior differential of A, if you look at A as a one form. Or if you can think in dimension 3, it would be the rotational of A, the magnetic field. Okay. Also, basically, we are going to use the same ideas to move into time domain, and the time domain problem is going to remain exactly the same you have here. Okay, so let me state the main result that I wanted to tell you about. So if we have taken orthonormal basis in Rn, we assume we take pairs of potentials, A1, A2, Q1 and Q2, smooth and completely supported in the ball of radius 1. And we also add this technical restriction. So we are going to ask that the nth component of the potentials, vector potentials, the magnetic potentials, when integrated in the xn variable, in the last variable, is equal to 0. Okay, we are going to ask this. If this holds, then if the fixed and scattering data for the pairs A1, Q1 and is equal to the fixed and scattering data for the pairs A2, Q2 for all directions in the basis and also the opposite directions, so we have plus minus Aj, then the exterior differentials of A1 is equal to the exterior differential of A2 and Q1 is equal to Q2. Okay, so you can see here that this is a result that involves 2n measurements in the sense that I defined above. So before in the first results of Nico and Rakesh that I stated, we had that one needs two measurements to recover the electrostatic potentials. Now that we have a vector with n components, extra components, we need 2n measurements. Okay, so this could one could think that maybe it would be necessary to have 2 times n plus 1 measurements, but what's happening here is that gauge invariance is actually reducing here 1 degree of freedom. So in the end, one needs only 2n measurements. Okay, so one of the main difficulties here in this kind of results is how to decouple the information about the magnetic potential from the information in the electrostatic potential Q. So things are very badly coupled, and this is one of the main obstacles when trying this kind of results. So actually, this condition that we need to add on the potential is at some point necessary in the proof in order to get this decoupling and be able to recover also the electrostatic potential and separate this information from A, as we have here, this condition. Okay, so we also have tried different results. So what we have tried also is to try with a Hamiltonian, sorry for going back, instead of trying this magnetic Hamiltonian, taking a Hamiltonian that just has one first order term, like here, and then fixing completely the zero order term. So here we put some a priori known function v that is fixed. So it is known, we don't need to recover that. Okay. So in this case, the problem changed quite a lot, among other things, because gauge invariance breaks. We don't have any more gauge invariance. And actually what happens is that making the same number of measurements, the same measurements, 2n measurements, one can actually recover completely A1 and A2. Okay, so it gets A1 equal to A2. And since we don't need to decouple information to get to the zero order term, that is not necessary to assume this assumption here on the integrals of the nth component. And the last result that we have worked on is to look in basically state that if we have some kind of symmetries in the component of A, or we have symmetries on Q, then we can reduce the number of measurements, sometimes to only n measurements or n plus 1 measurements, in the spirit of the results that I told you before with the symmetries. Okay, so I'm not going to go into these results here, but I would like to speak a little bit about the proof of the theorem I have just stated. And the idea is to use the equivalence with the time-dependent problem. So the statement would transform. This would be exactly the same. The previous theorem is equivalent to proving this, which is completely the same statement, except that we have changed here for the time-dependent equation. So if we have that all these solutions with the deltas incoming from all the directions of the basis vectors, and we know that these solutions are always equal in the surface of the cylinder, then the differentials must be equal and Q1 is equal to Q2. Okay, so as I was telling you, one of the main difficulties is the coupling of A and Q. So to see this, let's take a look of how actually behave these delta waves that we are sending here. So take one general omega in a unitary vector, and we look to the solution of this problem. So these solutions always have this structure here. So it's going to be a function times the Heaviside function, and then we have the delta wave times this exponential. One can prove now that there is uniqueness of solutions, and they have this structure here. This function psi is an integral related to the magnetic potential. Okay. Now the important thing that is this function v is going to satisfy always the wave equation and in t bigger than x dot omega, but the restriction on gamma, the plane on the cylinder, and this is what appears in the Kahneman estimate in the left-hand side, is really, you can see that you have this expression coupling Q and A in really bad way, because C also depends on A. So this is quite an obstacle in order to try to get to the unique result. So the main idea to try to solve this is the following: is to forget about using these delta waves and change, and instead of maintaining the same equation that we have here, we just try sending waves in which the initial data is the Heaviside function here, h, instead of delta. Now, since delta is the time derivative of h, and the A and Q doesn't depend on time, actually these solutions are time derivatives of these solutions. And since the data is in the cylinder, the data for this equation is also a time integral, or the data for the delta that is a time derivative of the data for UH. So actually, we can freely do this. These both equations are completely equivalent for the inverse problem. And why this is an advantage? Well, if you change to these H waves, the structure of the solutions is the following. They are always some function times the Heaviside function, and where U is a solution of the wave equation again, and the restriction on gamma of this solution now only involves the magnetic potential. So now we don't have anymore the electrostatic potential. So this is key to try to decouple information of both the vector and the magnetic potential and the electrostatic potential. So in the proof, the first step would be to prove this equivalence between the H waves and delta waves, which is not more complicated than I have told you in these few words. So then the The second step would to try to make a change of gauge in the potential, for example, A1, because we can freely change the gradient always, and this is not going to affect the problem, in order so that we have that A1 minus A2, the nth component is always 0. Okay? This is not possible in general. There is an abstraction of doing this, but the fact that the data of the waves coincide in the boundary, one can see that that actually you can remove this abstraction, and if the data of the solution is actually 0 at the boundary, this means that you can do this for the potentials. Okay, and this is what I meant by reducing 1 degree of freedom of the gauge invariance, because we now have that these vectors, the difference at least, has 0 nth component. So it's something that we don't need to recover. Okay, and it's useful also that in this gauge, since the potentials are compactly supported, it's basically equivalent to have that the exterior differentials are 0 than to say that A1 is equal to A2. So instead of trying to get this expression in the Kaleman estimates, we just can work safely with the magnetic potentials, which is easier. Now, there are also some technical things about the construction of the pseudo-convex wave that I will skip because of time. And basically, in the final thing I will tell is the following. Well, first one is also to adapt all the Kaleman and energy estimate methods for the first order perturbations. And this leads to an estimate. Kaleman estimate is very similar to the one I showed you before. And we are, as before, going to apply these Kaleman estimates for functions W that are basically a difference of solutions for the different pairs, A1, Q1, A2, Q2. Okay? So to finish, well, first, sorry. In the right-hand side, we have this term that involves an integration over the interior of the cylinder. And this can be bounded basically by the difference of the potentials, because we are applying the operator to a difference of solutions. So this is not difficult. And the thing is that these potentials don't involve the time variable. So we get a time integral, because we were integrated in the interior of the cylinder, a time integral of the weight here. And one can see that basically this gives the advantage of some small constant in the parameter sigma. So we get this function kappa sigma that goes to 0 when sigma goes to infinity. So the idea now is we apply this Kaleman estimate for the H waves, taking omega all these directions. And we take W, the difference of solutions we get, and the opposite one, we get also the difference, but of the opposite solutions incoming from minus omega. And this will yield the following estimate. You can control the component along omega of the difference of the potential by this. And recall that this is something that goes to 0 with sigma. So adding all the estimates for all directions, since the nth component of A vanishes, gives you control of A1 minus A2 in terms of Q1 minus Q2. So this is the big advantage of using the H waves, the Heaviside function waves. Now, for the last direction, we now do the reverse idea and we use the delta waves, because one can see actually that what we have now in the left-hand side with the delta waves can be related to the difference of the potentials. So basically, using the delta waves, we get the opposite estimate. Now, Q1 minus Q2 is less or equal than something small, and here we have the difference of the potentials. So finally, combining these two estimates, the estimate that comes from the H waves and the delta waves, gives you that both pairs of potentials must vanish. Okay, so I'm sorry about the time, but with this I will finish the talk. So thank you very much.
Thank you very much. Very interesting, very clear, very nice talk. Thank you very much. Now we have time for some questions or comments. Is there any question?
Yes, one question, Cristobal.
Okay.
Yeah.
Can you say something about the construction of the weight function, or how is it? Has to be convex or any?
Yeah. In order to have Kaleman estimates for the techniques for the wave equation. Where is this? Here. One needs strong pseudo-convexity for the weight with respect to the wave operator, and one also needs quite a few more properties. Among the most important one is that the difference. That the weight must decrease quite rapidly as you go from this plane here. So it must be strongly pseudo-convex, but it needs to decrease in time. So that's one of the difficulties one has, because one basically needs this in order to forget about the terms that involve integration here and here. And to get some useful properties about the time integration of the time integral of the weight. That's basically it. There are also, for the magnetic case, you need also this weight that even if this weight depends on omega, you need also that always that the restriction on gamma is a function independent of omega. This is actually not difficult to obtain, but is necessary to combine different directions, Kaleman estimates in different directions. But okay, there's.
Thank you.
Thank you. Any other question or comment? Okay, I have a question about for both problems, for the magnetic and non-magnetic cases. Your observation is for a certain number of directions. You know you observe on the whole sphere. I mean, for all theta in the n-1 sphere. This is your data. So are you able to say something if you only have a partial observation? I mean, do you have uniqueness in some cases if you only know AQ for some theta and not for all theta? For theta, for example, on the semi-sphere or a quarter of a sphere, I don't know.
I'm not sure.
Studied anywhere?
I really haven't thought about that. I don't know if someone has some partial data in that sense. I really don't know what happens if probably one needs to use techniques of Kaleman estimates. I really don't know if there are results in that sense. I don't think so in the fixed and scattering problem, but maybe they are. I don't know.
Okay, thank you very much. Okay, we are going to pass now to the second talk in the afternoon. So can you please share your slides
yeah, of
again?
Course. Okay.
How I need to interrupt my sharing? I don't know how to do that.
I think you have to stop sharing.
Okay. And how do I do that? Sorry.
I think it's the same button.
Okay.
Stop of sharing.
It looks like I have stopped sharing. But
yes.
It's working?
No, you're sharing.
You're sharing.
I don't know why.
You're still sharing, yeah.
So you have, vete abajo, en la parte de abajo.
Sí, pero es que no consigo cargar ahora Zoom.
Ahora. Ya lo detuve.
Vale, perdón.
Ya lo corrí de la charla. No, no es esto.
Vale, gracias.
No,
perdón.
Gracias.
Okay. So, can you hear me?
Yes.
Yes,
okay.
Perfect.
And can you see the screen?
Yes.
Yes.
Perfect.
Okay.
So,
thank you. So you are going to give a talk with the title Quantitative, Rapid, and Finite Time Stabilization of the Heat Equations. Okay.
Yeah, definitely. Thank you for the introduction. At first, I would like to thank you, Eliza, for this invitation. It's really a great pleasure to give a talk. And also thank the previous night's talk. It's insane, it's very good. So today we're going to talk about stabilization problems, more precisely for the heat equation. Here is the heat equation. You get open connective boundary domain where you have your heat flow somehow, and you're able to control the evolution of the system through a subdomain. As we know that heat equation is one of the most studied items in mathematics and control theory, which implies a huge rich theory out here. So here I just summarize some essential ideas. It looks like a little bit complicated, but it can be decomposed by parts, first part, second part, and second part. So essentially, at the very beginning, it is about the observability problem, where you also find unique continuation and using the tool of macro local analysis. And secondly, it would be like exponential stabilization. Of course, there are many other stabilization techniques. Here I just emphasize most famous Riccati method using optimal control theory. And then I move to the more recent finite time stabilization, rapid stabilization, where you get a very powerful tool called backstepping. So by combining all those parts together, you get nothing but a previous picture. Probably you have already noticed. The more on the left-hand side, the more theoretical it is, and the more on the right-hand side, it becomes more and more constructive and automatic. Today we can cover all of this, but not limited to that. Otherwise, it becomes a reading group. So here we go. Essentially, we find some new connection, new link between those classical theories. It starts from a Neapolitan approach leads to rapid stabilization. And surprisingly, using this kind of Neapolitan approach plus spectral inequality, it yields quantitative rapid stabilization. And armed with this kind of quantitative stabilization result, I'm able to give a new, totally constructive proof of law controllability, having optimal costs, and more importantly, it works perfectly for nonlinear systems. And lastly, I'm able to finally prove the finite time stabilization of multi-dimensional heat equations to be compared with one-dimensional case in the literature. So briefly, we have those beautiful, satisfying classical theories about rapid stabilization, about law controllability, about finite time stabilization. And then in this talk, we gotta go further, go beyond. We get quantitative rapid stabilization via explicit field by null. We get totally constructive proof of law controllability having optimal costs. It works perfectly for nonlinear systems such as Navier-Stokes equations. We get finite time stabilization of multi-dimensional heat equations. Of course, it also works for Navier-Stokes equations. So in the rest part of this talk, you could be given by two parts. The first part, I would say somehow like a review session. So I get to show you those beautiful classical satisfying theories. And the second part would be, let's say, a new part. We get to present the new stuff. So here we go. We start from the observability problem about operator theory. Suppose I'm giving you this kind of your favorite control system in your classical fashion. I'm asking you a question about controllability. A natural way will be, okay, I get to solve this question explicitly and find the optimal candidate. I would say like this works perfectly, but only if you can solve this equation. In some case, you cannot get the explicit solution for Navier-Stokes equation, for example, which is not the case. And here it comes the revolution. Jacques Louis and his masterpiece Hilbert uniqueness method. So once and for all, he built a bridge between controllability and observability. Once and for all, you only need to solve the observability problem for controllability. So what is observability? Suppose I give you a linear differential operator and you need a function, and you know that this function equals to 0, and you know there's some information about the function in a small domain. And I'm asking you, can you actually recover all information in the whole domain? A quantitative version of this kind of problem is called observability inequality. And if the case that the function taking value as 0 is called unique continuation or propagation of smallness. And I would say that's exactly the reason why micro-local analysis Homander school entered the game. This is nothing but exactly a local version of the previous picture. It's a local version here. You see here, you get a hypersurface. You know that after below this hypersurface, the function taking value at 0, you want to propagate this smallness beyond this hypersurface. And there's essentially a long history behind this kind of problems. It starts from analytic sighting, goes to canonized innovation until Homander's breakthrough, and then you get wave operator. And now people working on some quantitative estimates, they work on degenerative operator and also measurable sets, extra. But considering this kind of Kahneman estimates and observability, it is well known that in the golden 90s, there are two methods appear at the same time. First one using global Kahneman estimates, and second one using local Kahneman estimates. I'm sorry, I'm not able to, I say, to conclude the people who have made contribution to this or this field, because if I start by Lobo-Joviano, Fusco-Villamanoff, I go to Joao and the Pure and Fernandez Caja, Duke, Kahibusha. In the end of the day, everybody should appear on that list. So never mind. And eventually, I also want to emphasize the spectral inequality. This is nothing. This is just spectral decomposition. You know, this is Laplace operator. You get eigenfunction, eigenvalues. And then spectral inequality is a quantitative estimate on the low frequency energy. So this is the low frequency energy. This is a combination of low frequency eigenfunctions. And then spectral inequality is something that you get this quantitative. Sorry? Okay. I continue. I continue to the exponential stabilization part. Of course, there are many exponential stabilization techniques, but here I just want to emphasize probably the most famous Riccati method. So eventually we are able to deal with more general parabolic equations. And of course, you can still perform your favorite spectral decomposition. And then having a look at the eigenvalues, there are two kinds of eigenvalues. You know, the one have positive real part, the one have negative real part. So naturally, you can be decomposed by stable eigenfunctions, unstable eigenfunctions. If we have a look at the evolution of the equations on those stable and unstable manifolds, what do we have? We know that on the stable part, it is very well. It decays, it is stable, but it is of infinite dimension. And then you get the unstable part, it could behave very randomly, badly, but good news, it is of finite dimension. So I assume you agree that we only need to stabilize the finite dimensional unstable part. And here comes the Riccati method. Wow, it looks like a it looks like a little bit complicated, but it's not. It's something like systematic and very powerful. So at the beginning, you only work on the finite dimensional unstable part. Of course, you can find a control term that the open loop system decays exponentially. I mean, here is just using control, not feedback. And you agree that the stable part is also stable, so you know that whole system decays exponentially. And then here comes the tricky part. That's the core of the Riccati method. It proposes you to study the extent of the Riccati equation. And the solution of this Riccati, this kind of optimal control problem, and the solution is given by this kind of Riccati equation. And by solving this kind of Riccati equation, you are able to construct a feedback null which stabilizes the system in the closed loop system. I know probably I'm going a little bit fast, so I would simply suggest you to remember one simple fact is like here you always get this kind of nonlinear algebraic complicated Riccati equation to deal with. I move forward to a more recent backstepping and finite time stabilization. So what is finite time stabilization? Probably you can simply imagine as null controllability in a stabilization sense, but of course the definition more difficult and is a little bit different. So more precisely, you want to construct a feedback null such that solution becomes zero after any interval of time greater than t. And plus you also need to satisfy some uniform stability property. And there is actually a project behind all this, which is called Finite Time Stabilization Project, which I have been working for 5 years. It's like you want to stabilize the finite time null controllable system in finite time. This is very natural in one hand because finite time stabilization, of course, give you finite time null controllability. So essentially, we want to contribute on the other way around. And we want to find some systematic method to do that. Let me take an example of KDV to explain you about the finite time stabilization and also the backstepping. This is a one-dimensional model, very famous model. And if you have a look at the linearized system and assume that there's no control, then by performing our favorite energy estimation, we know that the system decays exponentially. Or indeed, it's exponentially. Here you can simply see that it's asymptotically stable. But in any case, the decay rate is bounded. And we have a look at another system. This system actually decays even faster, thanks again to the energy estimation, thank you to the dumping term here. So a question would be, if I have a bad system of y decay not that fast, we get a good system of z decays much, much faster. Can you actually find the feedback norm such that we link the function of y and the function of z together? And the solution is called backstepping. It corresponds to find the feedback norm. Of course, you always need to find the feedback norm, and also bounded linear invertible transformation such that the flow of y is mapped into a flow of z. In that sense, the flow, the solution of y have the same stability as the solution of z does. So of course, you get rapid stabilization. And in this special case of KDV, the backstepping was studied by Cohon and Safar. They used some kind of Volterra transformation. It looked like something like convolution. And in order to do this, you need to get a curl function which satisfies this kind of curl equation. So by solving this curl equation, you get K. By get K, you get Volterra transformation, backstepping, and rapid stabilization. But how to pass from, say, rapid stabilization to finite time stabilization? As you can see here, for every lambda, we can find the backstepping, we can find feedback norm such that the system decay exponentially fast. So of course, you can find the time t such that energy is divided by 2. So I'm wondering, okay, so this is the time interval 0 to t. Is it able to decompose the time interval into many parts? So the first part, I get number 1 and t1, number 2 and t2 and extra. So you get each part the energy divided by 2. So you get 1/2. You get 1/4, 1/8, and then you can still converge to 0. So in order to do this, the only requirement is like the sum of the time interval is smaller than capital T. And it can be guaranteed if you can have a good estimate on the transformation. And to do this, you have to get log controllability, and you can also modify the feedback norm to get finite time stabilization. And in this special case, in this slide, I just provided a good enough estimation, which leads to the finite time stabilization. I'm not going to talk about details of the estimation. So I guess this is the end of the review session. So we get to talk about those new stuff, finally. The motivation was like I want to solve the finite time stabilization problem of multidimensional heat equation, because in the literature, it was only solved in one-dimensional case. So it turns out to be a quantitative rapid stabilization problem. But talking about rapid stabilization, you got to think about what? You got to think about backstepping, you got to think about Riccati method, and of course, there are some other methods. And so at first, I decided to have a look at the backstepping. You know that backstepping is definitely a huge success on one-dimensional model. You get Schrödinger equation, water tank, KDV, burgers, degenerate operator. A lot of people have contributed this, including my good mate, Cristobal and Amohi Hayat. I also want to emphasize the group of Riccati. They introduced some kind of time-varying curl equation, which solves the finite time stabilization problem also. But there's only one simple common fact. It's like, this is only one-dimensional models. What about multi-dimensional models? A lot of people have asked this question, and it turns out to be a very, very challenging problem. Even Jean-Michel thinks it's very challenging. So I would say this is definitely a very good open question. And never mind, I still get a Riccati method if you remember. I come back to Riccati method, but if you remember well, you always get this kind of a nonlinear algebraic complicated Riccati equation to deal with. Now it is simply my own feeling. I think it's more difficult. I think it's hard to get quantitative estimates. And besides, there are some regularity issues that I don't really like it. But of course, it is only my own feeling. So it's like a little bit depressing, On one hand, it was like Jean-Michel. On the other hand, it's my own feeling. So by between Jean-Michel and me, I didn't choose to read it myself. I think maybe there are more chance for Riccati method. So I decided to dig into the Riccati method, check every details, and of course, you meet some technical problems. I asked the expert Emmanuel Trainer for this. He was very, very kind. He not only solved my technical problem, and he also told me that, actually, there's another stabilization method, which is more explicit. And this method belongs to him and Jean-Michel. There's always Jean-Michel. I'm not surprised. So I decided to have a look at this new method. It was like a method introduced by Jean-Michel and Emmanuel Trainer. They want to solve some global controllability problem of nonlinear heat equations. You know that this nonlinearity is really the prime of Jean-Michel. So I highly recommend this book. I've been reading this book for 5 years, and almost every day I keep benefiting from this. So if you want to have a look at know more about mysterious return method, power series expansion, quasi-static, don't hesitate to have a look at this book. And more importantly, this is for free. So let us come back to the stabilization problem. They want to have a look at, they want to stabilize this kind of a system. So they perform some standard variation, linearization, simplification. In the end of the day, it's sufficient to stabilize this kind of system. And they also perform the spectral decomposition. They get stable part, unstable part. They also perform moment theory. This is a decomposition moment theory. Each moment satisfies a very simple ODE equation. And now they decided to define a new stuff. They defined the unstable part by new variable. It satisfies ODE control system actually. And there's a little bit tricky part. They say that, okay, we know that function of y is controllable, then the function of z is controllable. Then of course, xn is controllable, which means that the ODE system satisfies Kahneman condition. And using Kahneman condition, you get this matrix identity. I would call magical matrix identity. It looks like a little bit, say, weird. But if you have a look at this Neapro function and you take time derivative, you get nothing but exactly the magical matrix identity. And after some computation, you can get exponential stabilization. I would like to emphasize that in this procedure, the decay rate is assumed to be very small. So by looking at this, I really get a feeling that it should be the same for multidimensional heat equations. So I take my favorite multidimensional heat equation, it's like this. And I also perform spectral decomposition. And now I decide to define the stable part and unstable part by new stuff. And you know that this is the heat equation. This is the heat equation. And you know that the control term is assumed to be compactly supported in that small domain. So what does it mean? It means that you have an infinite dimension of degree of the control. But I think it's a little bit too much. I think maybe it's sufficient to get this. Maybe I get motivated from Riccati method, I don't know. So that's the reason that I also need to decompose that part, which is that part. It's nothing but simple calculation. And I also define, as Jean-Michel and Emmanuel, I define this kind of stuff. This is nothing but eigenvalues. I get a very, very simple ODE control system. And Jn is also explicit. It comes from the decomposition of chi omega ej. And now I decided to change a little bit the strategy, because in Cohon-Trenan they use kind of controllability, but now I think it's not necessary because using unit continuation, you can also get that the Jn is invertible. And then you can also prove that it satisfies Kahneman condition. And we come back to the case of Cohon-Trenan, we get Neapro function, we get exponential stabilization, we get magical matrix identity. But the real question is, how can we get a quantitative rapid stabilization? So I decided to, conclude what have no, we get somehow explicit matrix. And now I decided to make life as simple as possible. I decided to take the control term, the feedback law as simple as possible. This is nothing but the projection of a low frequency. And this is very, very simple ODE. And if you have a look at the construction by Cohon-Trenan, here it's very good, but it's not still not that satisfying because, okay, this is known, but you still get Qn and Kn to deal with. You need to calculate this kind of stuff. And me, I want to make life as simple as possible. I think, okay, let me have a look at this Neapro function. This is really simple because this is just low frequency plus high frequency with different kind of weight. I get no idea about what would happen, but let us try. I take time derivative of the low frequency, you get this term plus this term. Now I think, oh, it's great because this term, this is negative. So if it is negative, I don't care about it. So essentially, eventually, I only need to care about this term. This turned out to be a quadratic form. So I have to estimate a quantitative quadratic form. By looking at this quadratic form, I get a feeling like it looks like something. It looks like some combination of low frequency energy. So suddenly, it really reminds me about spectral inequality. Having a look at spectral inequality, you see, combination of low frequency energy, combination of low frequency eigenfunction. And it turns out that quantitative quadratic form, it's exactly the same as spectral inequality. Proof is easy. Quadratic form, you get double sum, you get inner product, you get this, and this is exactly spectral inequality. You see, this is very easy. It's not even proof. Let me call it a fact. Somehow it reminds me about a story by the great mathematician Jean-Pierre Serre. So like 3 years ago, in the Séminaire Bourbaki, Jean-Pierre Serre would like to introduce a theorem. So he started to write on the blackboard theorem, and he started to write a phrase, and then he stopped. By looking at this blackboard, he said, wow, I think the proof is very easy. So, and then he erased the theorem, says, let us call it a lemma. Okay, it's the same story here. Let us come back to our stabilization problem. In conclusion, we have a very simple feedback law. We got a very simple near-proof function, and we get also very simple. Okay, everything's simple. I'm sorry. Very simple ODE system and the feedback closed loop system. And I take the derivative, and now it's time to do some real analysis. This is a low frequency. This is a high frequency. I get to calculate this one by one. The low frequency is very explicit, and this is negative, so don't care. And this term I use spectral inequality, something quantitative. High frequency, this is just the identity, and also identity. And here I just want to remind you about one simple fact. It's like tau n plus 1 is bigger than lambda. So this can be smaller than the diffusion energy is smaller than this kind of energy. And this feedback law, I got nothing to do. I use Cauchy-Schwarz. And you know that you see this term and this term appear 2 times. So I use Cauchy-Schwarz again. So this term can be compensated by the formal one. And I also get the explicit form. I think it's okay. I would say this is finished. Why? Because here you get minus lambda, which is exactly what I want. Here, this term is a little bit annoying somehow, but you know, here you get a mu lambda, but here there's no mu lambda. So what it means by choosing mu lambda as large as possible, this term can be compensated by that term. So inspired by the preceding calculation, I have a choice of gamma, I get a choice of mu, and I do the same calculation, I get exactly minus lambda v. This provides nothing but quantitative rapid stabilization. And please forgive me to use the word elegant for this, because you see here, there's not even extra term. This is exactly minus lambda v. It's very interesting, very beautiful. So briefly, I get a very, very simple explicit feedback law, which provides you the strongest quantitative rapid stabilization result. And this feedback law has strong physical meaning, because this is nothing but the projection of low frequency energy. And I also want to emphasize the fact that we have benefit from the spectral inequality. But even if you don't know spectral inequality, from unit continuation, where you know that JN is positive, you can still choose this kind of gamma, this kind of mu, and it also needs you about rapid stabilization. But of course, you don't have this kind of beautiful estimates. So now let me quickly talk about null controllability of optimal costs. If you remember well, okay, you see that we have already get the quantitative rapid stabilization. If you remember well, the piecewise argument somehow by the backstepping, of course, we can get a constructive proof for null controllability. But this is not finished yet. Because I followed an advice from our organizer, Fernandez Caja. It was like during my PhD studies defense, he said, okay, I find that what you've done is really explicit. So can you consider about the cost problem? I say, wow, it's a good idea. So let me have a look at this cost estimate. And check the literature. The cost estimate is something like, if you want to have a null controllability, you can also estimate the cost of the control term. And in the literature, it's something like the L2 norm of the control term is bounded by exponential c divided by t. And what we say the optimal is that t is of power 1, is not t power 2, not t power 4, is t power 1. And indeed, both the Bochovian and Fusikow-Riemann law leads to this kind of optimal cost. The Bochovian approach works for heat equation and also Stokes equation, and the other approach works for nonlinear heat equation, but it cannot give, and at least so far haven't given the optimal course for complicated systems such as Stokes equation and Navier-Stokes equations. So I think what I've done is really explicit. So I think maybe we can also get optimal course from this kind of stabilization approach. And after 1 day, 2 days, 3 days, I forget. And I simply provide this kind of simple construction. You C1 from spectral equality, you get C2 from C1, you get Q from C2, and you get C3 from Q. And even each choice of Tn, each choice of lambda n is totally quantitatively explicit. And you can do some performing some simple estimation. You find the L infinity L2 norm of the cost estimate of the control term. You also get this kind of optimal course. And plus, I also improve a little bit the L2 estimate in the literature. So briefly, I get a totally constructive proof for null controllability of the heat equation in a slightly higher, stronger space. But this is not the most interesting part. Here it is. You know that the EPFL function energy estimate is stable under perturbation. It's stable under nonlinearity. What does it mean? It means like for nonlinear system, the same stability, same feedback law, same stabilization, same explicit construction, same optimal course holds the same. It means it holds perfectly for nonlinear heat equations. It holds perfectly for Navier-Stokes equations. Here I get optimal course, which improves the T⁴, T⁴9 stuff in the literature. And it definitely works for many other systems. And so in the end of the day, we can also solve as what I want to do initially. We can also solve the finite time stabilization of multi-dimensional heat equations. And I'm not going to talk about details, but after modifying a lot, some about the feedback node that we have constructed for null controllability, we can get explicit feedback node which stabilizes the heat equation in finite time, satisfying finite time stabilization and also uniform stability. Yeah, by the way, it's of course the same story for Navier-Stokes equations. So I guess this is really the end of this talk. I would like to emphasize a simple fact is like we have benefit from global energy and micro-local analysis. You know that these two methods are very powerful, and at the first glance, it is a little bit not that compatible. But you see, I'm very happy to see that this is a very simple, vivid example to show you that by combining this kind of different philosophies, we can also get some interesting questions. Yes, I got to stop here. Thank you for your attention.
Thank you very much for this very interesting talk again. Now we have time for some questions or comments.
Do you hear me? May I ask a question?
Yeah, of course.
Okay.
Of course.
It's Jean-Michel. So congratulations, very nice talk. I was wondering what can be done if the system depends on time also.
Wow.
Possible
this
to do
is
something?
really this is really something. To be honest, I haven't think about this, but this is definitely the next step. And if you ask me about it, I think we can do something, but you need to change a little bit the structure. You need to change the upper function, which probably depends on time. And then we need to get very strong spectral inequality for which depends on time. But I mean, it's like if the coefficient is C infinity somehow, I think we get a chance to get this kind of, uniform spectral inequality, which depends on time somehow. But I'm not sure. But this is definitely a very good question.
Any other question?
Yeah.
A comment? Sylvain?
Yeah, so I have one. So in fact, I'm not completely sure to have understood how you design the stabilization operator on the finite dimensional system. How do you do that? Is it the Riccati for the projection on the first eigenvectors, or is it?
Yeah. No, it's not Riccati. It's very simple. It's just a very simple trick. You see, this is so. I mean, for whatever I give you a lambda, you can have somehow the low frequency. I mean, this is a low frequency, and this you get a high frequency.
Okay.
And low frequency, you do nothing, you just do a projection. And then the tricky part is like I give you a very big weight, and it's very surprising. You do some calculation, it's just one page, and you get one quantitative representation.
And if you take the Riccati of the finite of the
No,
first eigenfunctions, will it give something or not?
Riccati, of course, give you something. Yeah,
it should be better in principle, right?
Riccati?
Yeah, it will give you the solution of the optimal control system. So, okay, maybe the conditioning number of the
I mean, it's Riccati is definitely a very
function is not so good, but it should be better, right?
Yeah, it should be better, but the problem is like you have to estimate this. Nobody has done. I mean, it's you have to give a quantitative estimate. Of course, probably it's better, but here I get an even simpler, probably simpler feedback. So, I mean, it could be better, but I mean, I think also there's a problem with regularity somehow. But yeah, it's a very good idea.
Okay, thank you.
Yeah, thank you.
There is a question by Victor Hernandez Santamaria. He said, I don't know if you can read it in the chat. He says, I have one question. With your method, what kind of nonlinearities you can handle for the heat equation? Global ellipses, polynomial? What kind of nonlinearities?
Let me see. But what does it mean by global? Okay. But I mean, I have applied for some at least for critical subcritical nonlinearity. For example, if you get your heat equation, I mean somehow like this. I mean, you of course it depends on the dimension, and then you can. I've only handled this kind of nonlinearity, but I'm not sure. I don't think the. Yeah, I mean this is definitely. I think it is stronger than global ellipses. Right? This is something. Yeah, so polynomial somehow. Okay, polynomial. So and for global ellipses, I guess so. I guess it's the same story. And I mean, it's by you get something like some y log y is. I think maybe we can also treat this kind of nonlinearity, because I mean this one is probably stronger, and also you get. I have also applied for Navier-Stokes equation, so I guess many systems.
There is another question by Drew Steves. He says, I'm wondering, many thanks for your excellent talk. I'm wondering if you think that your approach would be valid for coupled parabolic systems with first and zero order coupling, like those studied in the work by Lisi and Dupré.
I am not sure if I understand your question, because I assume that the work by Lisi, because to my limited acknowledgement, the works by Lisi and Dupré, they use some nonlinearity to do controllability problems. And here probably it's a little bit different. Here, I mean, I'm doing this totally linear stuff and stabilization. But definitely it's a good question to think about. I haven't think about. I don't even know about what literature about Lisi and Dupré, so I probably couldn't really answer the question. But thank you very much.
Okay, thank you. Well, is there another question? Okay, we are going to stop. We are going to end this session. Thank you to everybody for your attendance. Next week we will have Rafael